In this video, I'm going to be giving an introduction to Simulink and using Simulink to simulate dynamic systems. We're going to start off with a pretty simple example where we implement the transfer function for a system, and then we're going to simulate that system's response to a step input. We're then going to move on to a more complicated example where instead of implementing the transfer function for a system, we're actually going to implement the system model based off of the equations we get by applying first principles. So let's get started. So I have MATLAB open here, and I'm going to open up Simulink. And you can find this by going to the Home tab on the toolbar. If we just click this button, we'll have the start page. And to create a model, we can click here for a blank model. So now we have our blank model in this window, and this is where we can start creating our model using blocks. So the first thing I'm going to do is I'm going to actually insert an image that we're actually going to use to base our model off of. So here is the description of the problem we're going to be implementing. So we have our transfer function, g of s. And in this transfer function, we have two poles, one pole at -1 and the other pole at -3. And then, of course, in the polynomial form, we have a second order polynomial s squared plus 4s plus 3 in the denominator. So we're going to start by implementing this transfer function using these numbers. And then later, we're going to implement this transfer function using variable names. So we'll actually be able to use variable names within the Simulink model and define those in our MATLAB workspace. But let's start off with using these numbers. So the first thing we're going to want to do is define our transfer function block and insert that into our blank model. So there's two ways that we can find a block and then insert it into our model. The first way is by navigating through the library browser. So if we navigate to this top left and find this library browser button and click that, this will open the library browser in Simulink. And here we can find any block that we have installed for our system. On the left, you can see a list of all the different libraries that you have installed, the primary library for Simulink, and under this library we have several different options which organize these blocks based off of what their function is. So if we start off with these commonly used blocks, we can see on the right side here, these are the actual blocks that are included in this library. So we can see we have a block that gives us a constant value. We see we have a gain block. We have an integrator block. And notice that this block, what it's going to do is it's going to integrate the signal in the time domain. And MathWorks has given the symbol a 1 over s, and that's because integrating in the time domain is equivalent to multiplying by 1 over s in the Laplace domain. So this gives a nice, quick way to identify the block. If we scroll down, we see some more blocks that we could imagine are going to be useful. We have a block that performs multiplication and labeled product. And we also have our summing junction, which will come in handy with feedback systems. So we don't have any transfer function blocks in this menu. But if we go to continuous, you can see that we have different blocks at hand. We have a block for performing derivatives. We again have our integrator block. If we scroll down, you see that we have a block for implementing state space models. So if you have our model in state space form, we can actually implement it directly into Simulink. And here we have the transfer function block. So this is going to be one of the blocks we're going to use. So to insert this into MATLAB or into Simulink, we can just click this and drag it over into our blank model page. And we see that that is scaled down quite a bit. So I'm going to shrink this image and zoom in. Okay. Now there's actually a variety of ways we can implement transfer functions. So if we go back to the library browser and we look down a little bit, we also have this block called zero pol. And so this block is actually going to allow us to implement a transfer function based off of our knowledge of the poles and zeros for that transfer function. So I'm going to actually drag that into our model as well, so we can compare that. So we'll get into using these blocks in a second, but real quick, I want to show another way to search for and insert blocks into Simulink. So instead of navigating to the library browser, we can actually pull up a search menu directly in the model. So actually, if we double click the left trigger on our mouse, this is what we get. We have this little search menu pop up. The default, if we don't enter anything to the search, is to create an annotation. So if we actually click that, you can see that we can actually type text. So we can say that this is a label. And so this could be handy in kind of keeping your model organized, and also being able to present your model to others. So we can actually say, if we're working this transfer function, we can say that this is a transfer function. But if we actually want to find a block, we can go ahead and type something into the search. So let's say we want to find the transfer function block that we just implemented. So if we start typing TRA, we actually get several suggestions, and the top result gives us this transfer function block. So we can see that it's coming from the Simulink library, and it's in the continuous, organized into the continuous group, which is exactly where we found the transfer function block in the library browser. So if we click that, that then inserts that block into the model. And we see this is the same exact block. So that's two ways of inserting blocks. But now that we have the block, let's start using this and setting up our model. So starting with the transfer function block itself, this has a number of parameters that we need to enter, and we can access those parameters by double clicking on this block. So if we double left click, this brings up the mask for this block. So in here, we see that we have a number of fields that we can enter in values. And specifically, we see that we have a section for parameters. And so there's two of these parameters that we are going to deal with this transfer function block. We have first the numerator coefficients, and then the denominator coefficients. This transfer function block takes in information and generates a transfer function block based off of the coefficients and the polynomials for the numerator and the denominator. So if we look at the transfer function that we're trying to implement, we have 1 in the numerator, and the polynomial for the denominator is s squared plus 4s plus 3. So let's So with the numerator, we have 1, so that's going to work for us. And in the denominator, you can see that the default is 1 and 1. And what that gives us is a coefficient of 1 in front of the s, and then a coefficient of 1 for the constant. So if we change this, let's say we put in 1 space 4. So now we have 1, 4, 1 as a coefficients. We can apply that. And now if we kind of drag that out to make it a little larger space for it to show us the transfer function, we now see that we have s squared plus 4s plus 1 in the denominator, which corresponds to the coefficients that we specified. So to make it the transfer function that we need, we'll replace this 1 with a 3. And we apply that. And now we have our transfer function that we're interested in implemented in this transfer function block. Now we can implement this transfer function in the zero pole block as well. We have the information about where those poles are, and of course where the zeros are. There are no zeros. So if we double click this, we then get the mask for this block. So we have parameters. We have a parameter for the zeros, we have a parameter for the poles, and then we have a value for the gain. So this gain is going to be the constant number that this we would multiply this block by. So if we look at what's implemented by default, we have a 0 for we have a 0 at the value of 1, and so that corresponds to an s minus 1 in the numerator. We then have a 0 and a negative 1 for the two poles. So the 0 corresponds to an s, and then the negative 1 corresponds to a s plus 1. And then we see that the coefficient out in front of, well, it's not shown because it's 1, but if we change this gain, let's say we change this to 2 and hit apply, and then let's drag this out so it shows. We now have this 2 multiplying this transfer function. So this is not something we need, so we're actually going to remove that. And then, or actually we need it to be 1. Right. So let's implement the poles and zeros for our system. So let's look at the poles first. First of all, we have 1 in the numerator. We actually don't have any poles, so we're going to remove this 1 and leave the square brackets empty. And then down here for the poles, we have a pole at -1 and -3. So if we replace these and insert -1 with a space, -3, and hit apply, this gives us the 1 over s plus 1 times s plus 3. And this is exactly the transfer function that we're interested in implementing. So both of these transfer functions are actually going to behave the same now. But we're just going to be working with this transfer function block. So let's get this out of the way. So now we have the transfer function block. We need to do something with it. We need to give it an input, and then we need to send its output somewhere. So let's start with the input. We see that just to look at the anatomy of this block, we have this arrow kind of pointing into the block, and that indicates that we would supply an input signal in here. So if we drag that out, we kind of have this signal line, which is red because it's not attached to anything, so it's kind of giving us an error. And then we have this output here with the arrow pointing out. And again, it's not attached to anything, so Simulink is showing that as red to get our attention. So we're interested in looking at the step response for this transfer function. So we're going to want to find some way of generating a step signal. So let's search through the library. So let's double click the left trigger for the mouse, bring up our search tool, And let's start looking first. Well, there we go. There's a step as our first result. And it's coming from the Simulink library, and it's under the menu for sources. That sounds about right. So now we have this step block. And notice that it only has an output signal line. It doesn't have any input. That's because this is a source block. It's actually generating the signal, so it's not taking anything as an input. So if we look in this block, this is actually going to have parameters as well that we can specify. If we open up the mask for this block, we see that we can specify a step time. So this is going to be the time in the simulation at which we jump from the initial value to the final value. And then of course we have the initial value, the final value, and then a sampling time, which we don't need to worry about this time. So I think this is going to work for us. We'll, when we look at our outputs, we'll just keep in mind that we stepped at time 1. So we'll leave that at the default, and then we'll make the connection to our transfer function block. And to do that, we just need to maybe click on this output arrow and drag that to the input of the transfer function, or we could drag the input to the transfer function to the output. And then lastly, Simulink has been getting smarter each release, and actually if we have these pointing at each other, it actually generates the signal path for us, and all we have to do is click that and it fills in that signal line. So now we have the output signal line to take care of. So if we're going to want to look at this result, we're going to need some way of plotting it. So in Simulink, we actually have a tool called Scope that allows us to see the signals in the simulation. So, and this tool is extremely helpful for troubleshooting your Simulink model. So let's bring that in. So we'll search Scope, and then so now we have Scope, and it's coming from the Simulink library, and it's under the menu for sinks. And when we have this in our model, we can see that it takes an input only and does not give any output. And then that's what's meant by the sink. So it's a sink for the signals. So we're going to want to monitor the output of this transfer function, so let's make that connection. So now when we click on this, this is actually going to bring up a plot. So right now this plot is empty because we haven't generated any simulation data. So let's get rid of that, and then we'll see something plotted on that later. So here we have it. We have our transfer function. We're receiving a step input, and we're outputting that to a scope. So we're going to be recording our output from this the response. So to actually run the simulation, we can go up to the top here and click on the play button or the run button. So we click that, and then Simulink goes ahead and runs the simulation. And we get a tone from Simulink letting us know that that finished. This is a pretty simple model, so it went really quick. More complicated models, the simulation might take much longer. So now that we have had the simulation run, let's look at what we get with the scope. So if we double click the scope, we can see that we have some kind of result. And if we think about this, so we have this plot represents the output of the transfer function to a step input. And we see that it's 0 from the start of the simulation until time 1 second. And then that makes sense because we had set our step time from the step from our step signal to 1 second. And so it makes sense that we're not going to have any response until that time. After 1, we start to see a response to that step input. So we have the signal converging to some final value. And the shape of this output makes sense as well, because we have, although we have a second order system for our transfer function, we see that we have 2 real poles. So we're going to have an underdamped response. And so that's kind of what we see with these simulation results. You can also, so it might also be nice to be able to see the step signal on this plot as well. And we can actually set up the scope to view multiple signals at once. So if we go up to the little menu in this scope window, this little cogwheel, and click that, we have another number of options that we can configure this scope with. So the one that we're interested in is the number of input ports. So by default, it's 1. But if we change that to 2 and click apply, we now see that our scope block has 2 inputs. So we have the first input is still connected to the output of our transfer function, but we now have the second input that we can send a signal to. So we're actually going to connect that to our step input just by dragging and then dragging it to a signal line for that step input for the step signal. And so now when we click on this scope, we still just have the same simulation results we did from the last simulation. We haven't generated any simulation data. We generated simulation data for this scope, but we didn't record it. So we don't have that data to plot. So let's run the simulation again by clicking run. I double clicked, so I made it pause. There we go. So now when we look at the scope, we have these 2 signal lines. We actually see the first signal, the output, in yellow, and then we have our second signal input, which is coming from the step. So we see that we're jumping from 0 to 1 at time 1, and we see the response to that. So this is a very useful way to look at the data from the simulation and to perform troubleshooting. But one thing I want to point out is that in this scope, this plot, we notice that we have a horizontal and vertical axes that are labeled with values, but we don't have any axis labels. And likewise, we don't have any title. We could do quite a bit of work to put those into this scope block, but that's really not a very convenient way of generating a professional plot. So if we want to plot this data for it to be presentable in a report or in a presentation, we're going to need to do a little bit of more work. And the way I recommend is actually to send your data to the MATLAB workspace and then use the plotting functions in MATLAB. So we're going to want to work outside of Simulink to generate our plots. So let's go through that. Get rid of the scope. Okay, so to get to that point where we can work with the data in MATLAB, what we're going to need to do is to export the data that we generated in our simulation to the workspace. To do that, we can use a block called toWorkspace. So if we double click to search, enter to, we see our top result is toWorkspace. If we click that, we get this block that takes an input, and then by default has this name out.simout. and we can actually change that name. If we double click, we can see the parameters and we can change the variable name. So let's say that we want to output the output of the transfer function. So we'll name that output. So if we apply and hit OK, we now have our block, which is labeled out.output. So let's connect that to our output and then run our simulation again. So now that we've just run the simulation with this 2 workspace block in the model, we can go to MATLAB So back in MATLAB, we can see in our workspace, we now have a variable called out, and it's described as a simulation output. So if we double click this, we actually see inside of this variable, it has a rather complex structure. So inside this simulation output, we have several other variables. So first of all, we have output, and that's what we labeled our 2 workspace block, and that's described as a time series. We also have T out. Click that. That is our time, so that's the time of the out of this simulation output. And if we click on output, which is what we labeled our 2 workspace, we see that we have 2 fields. We have time and data. So if we look at this, we see from 0 to 1, we have 0, and that matches kind of the 0 response we had. And then after 1, where we have a step, we start to see values increasing for the output data. So if we wanted to actually use this, the way we would access that data is, so let's say we want to access that output. So say that out.output, which is the name we gave, and hit enter. So that the output from that, entering that, just tells us that that's a time series, and that has some internal structure to it. So we see that we have time, which is a 54 by 1 double array, and then data, which is a 54 by 1 double array as well. And if we want to access the time and the data, we actually need to go a little further. So let's type out.output.time and hit enter. And now we have our data for the time in the simulation. We do something similar for the data. So out.output.data here at the bottom, and hit enter. We then get an output of the data that we had from the simulation. So now let's work on plotting that data that we got from our simulation. So in the command line in MATLAB, we can enter in figure to generate a figure for us. That generates the figure that we're now working with. We'll minimize that. And we can enter plot, and this is how we can plot our data. So we'll plot out.output.data. No, we want to plot time. So we want to plot time by the data, or the data by the time rather. Out.output.data. And close that. And so now we're giving this plot function our data for the horizontal axis and our data for the vertical axis. So if we hit enter and then bring our figure back. So now we have our figure back, and we see that this data matches what we saw in Simulink. Now we're still missing labels. So let's go a little further in this command line. Let's give it a title, and we'll call this just output. Give it a simple name. Hit enter. We'll give the horizontal axes a label, so x label. And then, so this is going to be time. And then we'll specify units in parentheses. So in parentheses we'll put s for seconds. And then we'll close that and hit enter. And then we'll give the vertical axis a label. So this is label, or sorry, y label. And then we'll call this data. And then we'll just not specify units there. So we hit enter. And now if we bring back that figure, we now see that we have a title and we have labels for our two axes. Okay, now back in the Simulink model, let's look at implementing variable names rather than numbers. So remember we had this transfer function where we are giving specific values for the pole locations or the coefficients of the characteristic equation. But let's look at how we can implement variable names that will allow us to change these variables and run several different simulations as we vary these parameters. So, and the form that I want to implement is actually going to be the kind of general form for a second order characteristic equation. So we have s squared plus 2 times zeta times omega n times s plus omega n squared. So if we look at the transfer function that we've been dealing with, we can solve for what these variables are going to be. So omega n, omega n squared is going to be equal to 3. So we can solve for omega n to give us the square root of 3. And then for the s term, we can then solve for zeta based off of the value we found for omega n. And so we can use these values to verify that our simulation, that how we implement these variables matches the case where we specified the values of this transfer function within MATLAB. So let's double click on the transfer function block and look inside this mask. So if we want to implement these variable names, we can actually implement these directly in this Simulink mask. So for our second coefficient, we want to implement 2 zeta omega n. So let's type 2 times zeta times w sub n to represent omega n, space, and now we want our third coefficient, and so this is going to be omega n squared. So we'll type out w sub n to the power of 2. And so now for our coefficients, we have 1, and then 2 zeta omega n, and then omega n squared. So if we apply this, and then spread this out, might allow us to see what we've implemented inside. So to see this, we actually have to expand this quite a bit. So let's reorganize these signal lines a bit. There we go. So now we can see in the transfer function we've implemented these variables. So let's jump back. Well, first I want to point out that we now have this transfer function in red. So this is Simulink kind of giving us a warning that we have these variables. We haven't specified what their value is. So what Simulink is actually saying is, hey, these aren't, I don't have any data in the workspace to apply to these variables. And so if we try to run this, we actually get an error suggesting that we load a file into the base workspace or that we create variables in the workspace. So let's actually jump back to MATLAB. And in the command window, let's enter some values for zeta and omega n. So we'll say that zeta, we said that that was going to be 2 over 3 times the square root of 3. Hit enter, that evaluates that value, and then we see that in our workspace we now have a value for zeta. And now for w sub n, representing our omega n variable, we had the square root of 3. So square root 3. Hit enter, and that gives us that value, and now we have that in the workspace. So let's jump back to Simulink. So now back in Simulink, we see that we still have the little red highlight around our transfer function block, but when we hit run, that disappears, and we actually were able to run the simulation. So we have to run the simulation for Simulink to kind of update and to recognize that we have that value in the workspace. So now when we look at the scope, this was the data from the simulation we just ran. We see that we get the identical data to what we had before. So that's great. So that's how you can implement variables in your Simulink model. You can actually just enter them into the mask for each of the blocks. So now that we've implemented this transfer function block and implemented simulation where we apply step input and we record the output, and now that we've implemented these variables inside of Simulink, let's look at how we can set up a parameter study where we run several different simulations while we vary the parameters of that simulation. So the first thing we actually need to do is to save this Simulink model, and we can do that on the top left here, and we can save as, and I've already saved this as example underscore TF for the transfer function example. So let's go ahead and replace that. And so now we'll have access to this from, we can actually call this, run this model from MATLAB. So back in MATLAB, I've cleared my workspace, so now we don't have any simulation data left over from running our Simulink model. And now we're going to see how we can run the Simulink model from the command line. So the first thing we know we need to specify values for the parameters in that model. So we're going to need to load those into the workspace. So we had zeta, and we've run that command before, so we can just hit the up arrow to reach that. And then same thing for omega n. So now I've loaded those values, and now they're in the workspace. So now we're ready to run the simulation. So we type sim, which is going to be the function that runs the Simulink model, and then type in the name of the file that implements that model. So type in example underscore capital TF dot SLX. And now when we hit enter, that's going to run that model. And now we see that we have an output in our workspace. And now we didn't specify a name for that output, so it defaults to ANS. We can specify the variable that it outputs into by entering a command like this, where we have out equal to the output of this sim function. So now if we hit enter, we now have the variable out in our workspace that contains that simulation data. So now let's see how we can implement all of this in a script. So if we go up to the top left, we can open up a new script. And so now rather than implementing or typing in all these commands to the command window, we can save all these commands as part of a script. So the first thing we're going to do is we're going to save this script. So we'll save as, and then we'll give it a name, say example TF, and then we'll specify this as a parameter study. So there we go, we'll save. And now for our simulation, we can specify the parameters. So we need to specify zeta. So we had that as 2 divided by 3 times the square root of 3. And we can end that line with a semicolon to keep it from displaying the output. And then we can specify omega in. And this was square root of 3. And now we can run our simulation and store that in a variable. So we'll store that in the variable out. So we'll set out equal to sim, and then give the file name for our model that we want to run. So this example sub tf dot slx. So now when we run the script, we'll be specifying the value of zeta and then omega in, and then we'll be running this Simulink model and outputting the data into this variable out. So if we go up here and hit run, we see that we've now populated our workspace with zeta, omega in, and out. And so now let's plot that data to take a look at it. So we'll open up a figure. We'll plot that. So we want to plot out dot output dot time, and then out dot output dot data. So then we also want to give this labels. So let's specify a title, and we'll title this output like we did before. And x labels, or x label time in seconds, and a y label. So now when we run this script again, we'll specify these parameters, run the simulation, and run the figure after we finish running that simulation. So we saw that we actually had this window pop up, which plotted our data. So we have the title we specified, we have the label for the data and time, and then we have our data plotted here. So that's great. So there's a script that runs a single simulation. Let's say that we want to actually run a parameter study. So let's say we actually want to test different values for zeta. So to do this, we're actually going to have to run the simulation in a for loop. So let's specify a for loop. So we'll go for, and then specify our index I, and that will be from 1 to n, and n we'll use as the number of simulations that we are running, and then we'll end that for loop. So And then we'll also need to store this data in an array, an indexed array. So for each one of these simulations, we're actually going to store the simulation results into an index of the variable out. So now we need to specify some variables for our study. So we're going to say that we're going to run in number of times. So let's say we'll run this 3 times, and then we're also going to need in each one of these to change for each one of these simulations to change the variable zeta. So first we need to define an array for zeta. Now we've already defined zeta up here. But we're actually going to change that. We're going to remove this value and turn this into an array. So let's make an array where we go from, let's say, an underdamped case to a critically damped, and then to an underdamped case. So we'll specify an underdamped value for zeta. So we'll say 0.05. And then the next value is going to be critically damped, or a value of 1 for zeta. And then finally, let's plot the case where zeta is equal to 1.5. So now we have an array, a 1 by 3 array with values of zeta. And we're going to need to do this a little different. So let's specify this as zeta array, and then because our simulation reads the variable zeta, and so here we're going to make zeta equal to zeta array and then the index that we have. So now what we have is we have this array of parameters that we're looping through, and then we have our variable that the simulation reads, and then we're specifying the value for that simulation based off a certain index in that array. So as we loop through here, we'll be specifying the value of zeta and then running that simulation. So now when we run this, we get an error dealing with our plot. So we actually run into the issue where we need to specify which index in out that we are specifying. So let's first just set this up to plot the first simulation result. So we'll specify the index 1 for out, and now when we hit run, we get output for that first simulation. And so this output, this simulation result, this is coming from the zeta value of 0.5. And as we expect, we have this underdamped response. You can see we have overshoot and some oscillation, which is characteristic of the underdamped response. Now, if we want to plot all 3 of these results, we're going to do a little bit extra for this figure. So we're gonna have to specify that MATLAB needs to hold on to this figure when we plot. Hold on to each plot. If we don't specify this, or if we leave hold off, every time we plot something to this figure, it's gonna just write over it, and we'll lose that plot. So if we have plot on, we'll then be able to plot multiple plots, multiple data sets. So we can just copy this line for each one of our simulations, and then change the index. So we'll have the first one be from the first simulation, the second one from the second, and then the third plot from the third simulation. So now when we run that, this will give us 3 different plots. So we have, it just happens that the first one is in blue, the second one is in red, and the third one is yellow. But there's not really a way to distinguish that just by looking at this plot right off the bat. What we actually need is to include a legend in our figure. So back in our script, we can add that. So we'll type in legend and then specify the names for each one of these data sets. So for the first one, we'll say that we'll give this the name zeta equals 0.5. For the second one, we separate that with a comma. For the second one, we'll say that zeta equals 1. And then zeta equals 1.5. And now when we run this, we're also going to be plotting the legend with that. And there it is. In our plot, we have our data, and then we have our little legend that we can drag to a more convenient place. And it tells us which colored line is associated with what data set. So now we can see that the blue one corresponds to our undergant case, where we set zeta equal to 0.5. The red one corresponds to the data set where we had zeta equal to 1. And then the yellow one is associated with the data set where we had zeta equals to 1.5. So with this is a pretty good skeleton for running design studies. Generally, we're going to be running some model, but each time we run that model, we're going to be changing some parameter of that model. So in this case, we're looking at how the output changes as we change the value of zeta. We might also want to set up a design study where we change omega n, or we might even have our model implemented in terms of actual physical parameters like a damping coefficient or a value for the capacitance or inductance, or a mass. And so we can set up our model to include those variables, and then use this type of script to run that simulation for several different values of that parameter. And here we're just plotting those results, but you could of course do quite a bit of post-processing. So you might be interested in actually evaluating what the maximum value is, or some other variable that you're interested in. So for each one of these simulations, let's actually add that. We'll see what the maximum value is that we get. So we'll include a variable max value, max val, and we're going to need to specify an index to match the simulation it's associated with. And we'll set that equal to the maximum value that we get from our simulation output. So we'll specify that we're looking at the data from out.output. We'll close that. And we can, well, I guess we're not going to need to, well, okay, so what we can do also is plot that data as well. So we can make a figure for that, and we'll plot, actually we'll do a scatter plot. So we do scatter, and on the horizontal axis we'll specify the value of zeta. Actually we'll use the array, and then our maximum value that we got. So max val. And then we'll want to label this figure, so we'll copy paste the titles. So we'll say that this is the maximum value versus zeta. And then on our X label, this is going to be zeta, and that has no units, and we have the maximum value. Maximum value. So now when we run this, we're going to be running the simulation. We're going to be post-processing those simulation results to give us the maximum value. And then we're going to be plotting a figure for those post-process results in addition to a figure where we're plotting the simulation results themselves. So we'll hit run. And we have an error. So we have dimensions are not supported when to put them. So it looks like, oh, here we forgot to index the simulation results. So so now we're actually post-processing the simulation results for the specific simulation. So now when we run, we make it through. So now we have that second figure that we generated where we have the simulation results. And then we have a scatter plot with the maximum value versus zeta. And so we see we'd want to do quite a bit to, we probably have more data points in a realistic design study, but in this case we just have these three. So we have a value up here, and when zeta is equal to 0.5, we get a maximum value of 0.387. And if we look over here and inspect that, that matches up with our peak value that we got. And then for other values of zeta, we have both of these are pretty similar because both of these are basically settling out to that steady state value without any overshoot. So there it is. There's an example of how we can set up a parameter study where we're simulating a system in Simulink, varying parameters, and then post-processing, and then plotting those results in a figure. So with that, we'll move on to implementing a more complicated model in directly from the equations that we directly from our modeling equations. Okay, back in Simulink, I have this model open where we're going to be implementing our next example. So this next example is going to be a model of a buck converter. So this is a electronic circuit that takes an input voltage and then through a dynamic response is able to transform that voltage into a lower average output voltage. So the circuit is composed of an inductor, a capacitor, and then we have a resistor representing our load. And then as an input to the system, we have V sub I, which is the value, the voltage being generated by a voltage source. And then also included in the circuit is a switch, and that switch is going to be switching the input to this inductor between the positive terminal of the voltage source and the and ground. So these are equations that represent the system. So we're actually going to be implementing these equations in order to implement a model of this system. So we see that we have two differential equations, two first order differential equations that we're going to be implementing. We have an analytical expression for the current through the resistor, and then we have some expressions that we're going to be implementing that revolve around the switching action of the circuit. So we're going to do this in two parts. The first part I want to do is implementing the LCR circuit, ignoring the fact that we have switching. So in this little section, we're going to implement these first three equations. So let's start with the inductor current equation. So on the right-hand side, we have a subtraction happening. So we're subtracting the output voltage from the voltage at the switch. And so to be able to do that, we're going to add in a summing junction. So if we bring in the summing junction, we notice that we have, by default, we have two inputs, and both of these are marked with a positive sign. So but we can actually change that. So if we double click, we have this option to change the list of signs. We have a vertical bar and then two pluses. This vertical bar basically acts as a blank, and then allows us to kind of shift around the position of those input arrows. So if we delete that bar and hit apply, we see that our summing junction changes to where the inputs are coming in from the top and the bottom. So depending on what your block diagram ends up looking like, you might be able to make it look a little neater by messing around with putting blanks into here. So we'll put this blank back, and because we're going to be doing subtraction, we're actually going to change the second plus to a minus. So we'll apply that, and now we can see that we have a plus and a minus. And these signals, we can label these signals coming in so that we know what they are later. So we'll label this input to this minus as V underscore O for the output voltage, and then for adding, we'll label the signal V sub SW. So the output of that subtraction is going to be the left-hand side. So now we have this output, which is going to represent the L, the inductance times the time derivative of the inductor current, I sub L. And so what we're going to want to do is actually get a signal for the current itself. So in a way to kind of undo these operations and give us a signal line for the current, what we can do is we can divide by L and then integrate. So we take this signal and divide by L and then integrate. So we're going to insert some blocks for that. So the first one we want to do is divide by L, and we can do that with a gain block. So we'll insert a gain block, and then double click in here to change the gain. We're actually going to change this into a fraction. So we're going to be multiplying by 1 over L, and that's actually going to give us a division of L. So we'll be dividing this signal by L. So now the output of this gain block is now the derivative of the current. And so now to give us the current, we're going to need to integrate. So if we integrate or search for an integrator, we can see that we have Simulink in the continuous menu. So we click that, and this gives us the 1 over S block that we saw in the previous example. So this 1 over S is going to perform integration for us. And so now this signal line is going to be our I sub L. And so now this chunk of blocks actually represents this first equation. So let's move on to the second one. So for this one, we have a similar structure in that we're subtracting one current from another, and then we'll need to divide by C and integrate to be able to give us v sub o. So let's just actually copy this chunk. So we highlight and then Control C, Control V to paste, and we just change the parameters here. So instead of 1 over L, we'll divide by C. These signals are going to be, so we're subtracting I sub R, so this is going to be I underscore R, and then this signal that we're adding or subtracting from is going to be I sub L. And then the output of this is going to be V out, or V sub O, V underscore O. So now we have two chunk groups of blocks that represent these two equations. And now let's quickly compare what kind of signals we have for these. So we notice that the output of the blocks representing the inductor current, we have an output of the inductor current here, and then we have an input to this set of blocks being the inductor current. So we can actually connect these two because they're the same signal. So now we actually have the output of this integrator giving us the current, and we can use that signal as the input to this set of blocks. So now we can also notice that we have V sub O and V sub O here as well. So we can connect these as well. So now we have our output of V underscore O from the blocks representing the capacitor voltage equation, and that serves as an input to the blocks representing the inductor current equation. So next, let's implement the current through the resistor. So this is just an analytical expression. So we're going to be taking the output voltage and dividing by R. So if we want to do a division, let's use the gain block. And then we'll set that up to be 1 over R. And its output is going to be this I sub R. And then its input is going to be V out, or V sub O. And so we can connect its input to this signal line. And now we have all of our signals set up except for the voltage at the switch. One thing I want to do real quick before we move on is just to tidy up these set of blocks. And the tidying up I'm going to do is actually I'm just going to flip this gain block around. So if we want to reorient these gain blocks, or blocks in general, what we can do is we can right click and go to format, and then we see that we can rotate them either clockwise or counterclockwise, or flip them even. So for this one I want to flip it, and we see that now instead of pointing from left to right, we now have it pointing right to left. And this will let me kind of clean up these blocks where I have a much more direct path through here. So the last thing I'm going to do, just so we don't have the signal line hanging out in space, is I'm going to give this just some signal, some block to attach to. So I'm actually going to search for a constant. So in this block, we can specify a value. So in this case, the default was 1. I'll just leave that for now. So now we have a complete set of blocks. So now let's move on to implementing the switching. So for the switching, we have two equations. First is that we are calculating this t hat sub SW. And so this is representing the kind of the time or the fraction of time within a switching period. So you can see that we're taking t, the actual time, and taking the modulo of that with t sub SW, or the switching period. So this t sub SW is going to be our switching period. And by taking the modulo of t, what this is actually doing is finding the remainder of dividing t by t sub SW. And so we can think of this as we have some switching period, and if we divide that and find the remainder, that's the result of that is basically the time since the time that we've spent inside of a switching period. Because every time we pass the threshold of time for a switching period, it's going to restart over at 0. To turn that into a fractional number where it's between 0 and 1, we can divide that by the switching period as well. So let's implement that real quick. So let's first find a block to perform the modulo function. So we'll double click, type in mod, and actually the mod block is what we're looking for. It's just an abbreviation for modulo. So we're going to be taking the modulo of t and t switch. So we'll need some signal for the time. So we'll try searching through here. Let's try searching time. Let's see, we get timer, timestamp, time scope. There's not really anything we can use here. So let's go back and search for something else. What we actually need is a clock. So if we type in clock, we actually have a block, a source block that gives us time. So if we click on this, double click on clock, there we go. If we double click on that, we can look at the description of this block, and we see that it outputs the current simulation time. So that's exactly what we need. So we'll pipe that into the mod function, and then the t sub SW, that's going to be a constant value in our simulation, so we can just use a constant block for that. So we'll type in con and search and get constant, so we'll plot that in, and then double click in this to specify this value, and we'll specify that as t underscore SW. Hit apply and pipe that into mod. And now the next operation we need to do is a division. So as before, when we were doing division for these for this LCR circuit, we're using this gain block. That's not going to work. We can make that work, but we're actually going to use for the switching is a block that actually implements division where it takes multiple inputs. So whereas the gain block takes an input, multiplies that by whatever the specified gain is, this divide block is actually going to take two inputs and divide one by the other. So we're going to want to divide this result from the mod function by the switching period. So we can connect that back to the T switch. So now this output is going to be T hat. So we'll label this T hat underscore SW. So that's going to be our fraction of the switching period. So we use that fraction of switching period in this piecewise function. So this piecewise function is specifying that voltage at the switch is going to be equal to either the input voltage or 0, based on it being connected to ground. And the condition for that is based off of the fraction of the switching period. And then, so we're comparing that fraction of the switching period to this capital D. And D is going to serve as our duty for our pulse width modulated signal. And this is actually how we're going to be operating the switch. We're going to be operating the switch so that it spends some fraction of time connected to the voltage source and some fraction of time spent to the ground. And that's going to happen within a switching period. And that fraction of time is going to be specified by this capital D, what we can call a duty. So, so we're going to need to perform this, evaluate this inequality. So the way we're going to do this is actually by, we can insert a block that will make this comparison. So let's set this up to perform a less than evaluation. So if we start searching for less, we see that our top result is less than, and plot that in, and now we have a block that has two inputs and a less than symbol inside. So this block is going to take one value and then compare that to the second value. So for the second value, we need the duty. That's also going to be a constant value in our simulation. So we'll plop in a constant block and pipe that into the input. And then we'll need to change this to match the variable we'll be using. So we'll use capital D there. So now we have this output, which should represent our pulse width modulated signal. And actually, the output from this less than block is basically a true or false statement, is what this block is. And so its output is going to be like a Boolean. It's either going to be a 1 if it's true or a 0 if it's not true. So if t hat underscore sw is less than d, so this will be our first condition in this piecewise function. If that is true, then the output of this block is going to be 1. And so we can actually test that. So let's test that by inserting a scope. So we'll insert a scope and connect that up. Okay, so now before we run the simulation, we're actually going to have to specify these parameters and or load these parameters into the workspace for MATLAB. So let's go back to MATLAB and let's specify those parameters. So we have, just say R is equal to 1, C is equal to 2, and L is equal to 3. And then for our switching period, we'll say T underscore SW is equal to, we'll do a 1 second switching period. And then our duty, we'll say that the time that we spend on is 1/4 of the switching period. So we'll specify this duty as being 0.25. Hit enter. And now that will give us all of the parameters we need for the simulation. So if we hit run, that worked out. So we got the little jingle from Simulink letting us know it worked. And we don't have any red highlights on these blocks, so we're good. So now let's click on the scope and we actually see what result we got from this switching model. Okay, so we ran the simulation for 10 seconds, so we have several switching cycles here. If we can actually zoom in to look at a little more detail. So up here on the top, we can find the zoom drop down, and we can zoom in the X. So that lets us specify some point along here, and we drag crossed, and then that will zoom in along the x-axis. So now looking in here at time 0, we're at 1, and then it looks like we're switching down to 0 around 0.25, and that's perfect. That's exactly what we specified for D, or the duty. And then looking forward, it looks like we have this signal that's repeating, and it starts to repeat at time 1, and that's also perfect because we specified our switching period to be 1. So the time that it takes for the signal to repeat is going to be 1 second. So so that gives us a working switch, and we have this LCR circuit that models the rest of the system. So let's work on combining this. So so if we get rid of these to combine these, we'll kind of move over and reorganize this a little bit. Okay, so we're going to be specifying V sub SW some other way besides specifying a constant. So this is actually going to be our switch signal. So we'll remove that and then also remove the scope. Now, if we're going to have a switching signal, what we can do is, well, let's search for something that switches. So we'll start searching SWI, and it looks like we have several options. The top one being called switch. I have a few different other switches, but let's try this first one. So now this switch block, it looks like we have 3 inputs and 1 output. And it looks like this output is connected by default to the first input. And then the second input seems to be some evaluation of an inequality. And then the third input seems to be the input that gets transferred to the output, perhaps when this inequality evaluates as true. So this seems to be what we're going to need. So we'll connect that up to our V sub SW, and this inequality here, this is going to be, we'll need this to come from our switching algorithm here. So we can, first I'm going to just condense this a little bit. So we move this up and connect these. So we've now connected this to our conditional statement, and then these other 2 inputs are going to be the values that we are setting the V sub SW to. So we're going to need a constant value for the voltage source. So we'll say V sub I, and then for ground we're going to have 0. So we need a constant block, and in this constant block we'll specify this as 0. Okay, so now we got to figure out which inputs to connect these to. So by default, it looks like if by default it's connected to the first input, and it switches when this probably evaluates to true. Actually, let's check. We can actually pull this up, pull the mask up, and look at the description. So the switch passes through input 1 when input 2 satisfies the selected criterion. Otherwise, it passes through input 3. So it sounds like if this conditional statement in the middle here is true, or we're sending some value that's greater than 0, that will evaluate to true. under that condition, we're passing through input 1. So looking back at our equation, our piecewise function, when this switch is less than D, that's when we want to send the input voltage. If we look at what we set up here, this is going to give us a 1 when we want to be sending the input voltage V sub I. And so when this is true, when this evaluates as true, this is going to evaluate as true, and we're going to be sending in the first input. So we're going to connect V sub I to the first input, and then 0 to the second. So with that, we should be able to run the simulation. First, we're going to need to specify what V sub I is. We haven't done that yet, so that's not in our workspace. But let's also record the output of this. So we'll just plop in a scope here so we can look at it inside Simulink. So we'll connect that scope. We'll need to specify V sub I, so let's jump back to MATLAB. And in the command window, we'll say that V sub I is equal to, let's say 12. Hit enter. So now that shows up in our workspace. So if we jump back to Simulink and hit run, we were able to run successfully. And now if we click the scope, we see we get some kind of output. And this output is, so first of all, it generally looks like we have some kind of first order response or some over damped response. And then in addition to that, we have some ripple going on. And so this ripple must be coming from the fact that we're switching. So, so that looks good. Let's actually look at what we're actually getting for this V sub SW. And so let's copy paste another scope here, and we can connect that signal there. So we'll need to run the simulation again, and then click on the scope, and there we go. So so what we should be expecting is that for the first part of the switching cycle, we're at 12 volts. So we're connected to the source voltage. And that's what we see in this case too. So we're starting off with the source voltage and then going to ground for the rest of the switching cycle. So that's awesome. We were able to implement the switching correctly, giving us the signal we wanted at this point, and then that serves as the input we were wanting to give to this LCR circuit. So with that, we've gone through quite a bit. We went through how we could develop this model by creating a block diagram based off of these equations that we were given. We were able to do this for each individual equation and then connect the signal lines that corresponded to the same variable. And so that was able to give us a closed loop here. And then we're also able to implement switching by implementing this algorithm where we take a modulus of the time and with respect to the switching period and normalizing that by the switching period, and then implementing a piecewise function using this switch block. So that should leave you with a pretty good foundation for using Simulink.